Okay, I'm finally making a C2 rational functions video. So here it is. Okay, we got rational functions. So here's our first one. F of x plus 2 divided by 2x minus 5. Okay, so if we just check this out, we can see that it's degree 1 on the top and bottom. So we've got same degree on the top and bottom. So that's something we should notice right away. So let's just find the key features of this function. Okay, so key features. So let's try to find our vertical asymptote. So our vertical asymptote occurs when our denominator is equal to 0. So we never want our denominator to equal 0. So what we find is we'll get an asymptote there that the function won't pass through. So let's go ahead and set the denominator equal to 0 and solve for x. So we'll end up with equal to, excuse me, 5 over 2, or 2.5. Okay, so let's plot that. So 2.5 is right here on the x-axis, and the line's just going to continue up and down. So that's our vertical asymptote. So because a value of 5 over 2, if we were to sub it into this equation, would create a denominator of 0, we know that the function won't exist there. Okay, our horizontal asymptote. This is the one where we plug really gigantic numbers into x, or really, really small numbers into x, and we kind of see what the function will do. So it's kind of the wishy-washy one too. So just picture, I'm just going to try to explain this. So just picture plugging in a really big value for x, 1,000,000, or whatever that number is, 1,000,000 plus 2, which would be like 1,000,002, but anyways, it's kind of like 1,000,000. And then the bottom, we'd have 2 times 1,000,000 minus 5, which is pretty close to 2,000,000 minus 5. But I feel like the plus 2 and the minus 5 aren't really doing a lot when you think about really gigantic numbers. So if you were to do 1,000,000 divided by 2,000,000, and you put that in lowest terms, you could reduce that to 1 over 2 if you divide the top and bottom by 1,000,000. Okay, let's try that again. So let's say we picked a gigantic, even a bigger number, like, okay, I don't even know what this number is. I'm just gonna keep adding zeros over 2 times that number. Same thing on the bottom. It's always going to reduce down to 1 over 2. So when you put like really gigantic numbers in for x, keep reducing down to this value. The same thing happens when you put super small values in for x. It's going to always reduce down to 1 over 2. So it turns out a horizontal asymptote, if it's the same degree on the top and bottom, our horizontal asymptote is always going to work out to be the coefficients in front of the x values. Here, so our horizontal asymptote is 1 over 2. So right where y equals a half, that's where our horizontal asymptote is. And it's just because that's just like what the function does when the x values get really big or really small. So when you think about really small x values, you're like down here. And when you think about really giant ones, you're heading this way. So the horizontal asymptote just kind of tells us what's happening in the very ends of the graph. Okay, so we've got our asymptotes on there. Now let's try to figure out our y-intercept. So we know our y-intercept occurs when x is equal to 0. So let's just plug 0 in for x. 0 plus 2 over 2 times 0 minus 5. And if we solve that, we get 0 plus 2 is 2. 2 times 0 minus 5 is negative 5. So our y-intercept is equal to 2 over negative 5, which is some small number, 0 bigger than negative 1. So I'm just going to plot that, on here. And finally, let's try to find our roots, also known as our x-intercept, and that's when y is equal to 0. So if you take our expression and this time we set y equal to 0, and plus 2 over 2x minus 5, So if we're trying to solve this equation, we only really care about the numerator, because what's going to happen is we're going to multiply each side by 2x minus 5 so that those will cancel out, and then we'll multiply this side by 2x minus 5, but then 0 times anything is just 0, so really with 0 equals x plus 2. So like I was saying, we only really care about the numerator when we're trying to find the roots, or the x-intercepts. So that means x is equal to negative 2. So if we plot that, negative 2. So now you can graph our function. So we're going to be a horizontal asymptote up here, pass through our x and y intercepts, and then we're going to turn and we're going to approach the vertical asymptote. If you're not really sure what's happening in the other quadrants, you could try plugging in like a value of, say, 4 into the equation. So 4 plus 2 is 6. 2 times 4 is 8. 5 is 3. So that would equal 2. So then you can get an idea of like, oh, the graph's going to be in that section. And I know it's going to be approaching my vertical asymptote and then approaching my horizontal one. So that's what that rational function is going to look like. Okay, let's try. Let me try one that has a degree on the bottom. So let's say we had f of x equals, let's say it was x plus 1 over x squared plus x minus 12. So that's our rational function. So something we notice right off the bat is we have a higher degree in the denominator, smaller on top. So if we want to find our vertical asymptote, we do that the same way as always. We set our denominator equal to 0. That's how we find our vertical asymptote. Now looking at this, that's a quadratic equation. I can't solve that by isolating x. I'm going to need to factor it or quadratic formula. So it looks pretty easy to factor. I can just do x plus 4, x minus 3 equals 0. And then if I set each bracket equal to 0, I get this. And x is equal to negative 4, and x is equal to 3. So those are my vertical asymptotes. And if I want to find my horizontal asymptote, the last time it equaled the coefficients in front of the x's. This time that's not the case. So we have a higher degree on the bottom. So what's going to happen is, let's picture the same thing we did last time. It's going to be a little more complicated, but if x was a really gigantic number, like a million plus 1, a million and 1 on top, and then if we sub in a million on the bottom, we get a million squared plus a million minus 12. Okay, I'm back. I had to figure out what a million squared was. Haha. So, a million squared is a lot. It's like a trillion. 9, 10, 11, 12. 12 zeros is like a really gigantic number. So we got, oh, and then we had to add a million. So I'm just plugging a million in. On the top, I would have a million and 1 if I want to get real accurate here, which I don't because it's really not that different than a million. And then if I plug the bottom in, a million squared is a billion. And then if I add a million, just change that to a 1. So then, there we go. That's a trillion. Okay, I don't even know how to say that number actually. Minus 12. So anyways, my point is you have a really gigantic number on the bottom. So if you divide sorry, this is rough. Okay, if you actually divide that, you get this. Because I just had to do that on my calculator. That's right. So you know what that tells me? That's like kind of pretty much 0. So that's telling me if I plug a gigantic number in for x and I solve it, I'll get close to 0. same thing will happen if I plug a really small number in for x. So my horizontal asymptote is 0. And in case you understood none of that, that always happens whenever you have a higher degree on the bottom of a rational function, you're always going to get a horizontal asymptote of 0. So there you go. Okie doke. So Y-intercept. Okay, so Y-intercept, so that's where we set x equal to 0. All right, so let's do it. Let's find f of 0. So we plug 0 plus 1 over 0 squared plus 0 minus 12. Looks like that's going to be 1 over negative 12. So that's our Y-intercept. And then to find our x-intercept, we're going to set y equal to 0. So we got 0 equals x plus 1 over, who cares, because it's not going to matter anyways. So if we get rid of the denominator by multiplying both sides by x squared plus x minus 12, we just end up with this. And therefore, x is equal to negative 1. Okay, so I got my y-intercept, I got my x-intercepts, horizontal, vertical asymptotes. Let's graph this guy. Okay, so my horizontal, just kidding, my vertical asymptotes at negative 4 and 3. And my horizontal asymptote is 0, so that's really awesome to plot. And my y-intercept's a super small number, so I'm just going to stick it right there. And my x-intercept is negative 1. Whoa, so I actually have an x-intercept, which tells me, I'm guessing, that my graph is going to look like this, I bet. But if you don't really know, what tends to happen with these guys is if they have two vertical asymptotes, they seem to form a parabola in the middle, or sometimes like a cubic looking function, or a parabola that goes up. So if we're not really sure, we kind of know that it's going to form, you can just plug values in to test that out. So you can just, back to original equation, try subbing in 1, 2, 3, negative 3 in for x, or try subbing in x, and just plot a couple points to help you out. And then if we're not really sure what's going on outside of these vertical asymptotes, why don't we try plugging in a number like 1, 2, 3, 4, anything bigger than 3. Well, let's try 5. So if we subbed in 5, 5 plus 1 over 5 squared plus 5 minus 12, which will be 6 over 30 minus 12. I don't know what that is, but it's some positive number. I can't subtract. So I know that it's going to be up here somewhere. Not that high, but. So that just tells me that I'm going to have a graph that's over here. And then if I try the same thing for 1, 2, 3, 4, 5, say I try negative 5. Negative 5 plus 1 over negative 5 squared plus negative 5 minus 12. And I check out what that's going to equal. Negative 5 plus 1 will be negative 4. Negative 5 squared will be 20 minus 5 will be 5. Wait, what? 25 minus 5 will be 20. Minus 12 will be 8. Got that one. So that's going to be negative 1/2. Oh, weird. It's going to be down there. Okay, so when I plugged in negative 5, I got this value. I wonder if it's going to look like that when it Desmos it on my phone. Check my answer. Okay. Let's, you know what? I'll pause this. Okay, hey, I'm back. It does look like that. Cool. So we got it. So you can always use Desmos to check your answers, as I just did. Okay, so that's what our graph is. We found all our key features. Nice. And that is C2. Oh, one more thing. Because some of the homework had you doing stuff with like holes and things and oblique asymptotes. That's technically not part of this course. But oblique asymptotes are formed when we get a higher degree on the top. We had like x minus 9 over 2x plus 1 or something. We would get an oblique or a slant asymptote. And that would be found by I guess, long dividing these guys by each other, which you don't need for this course, but just to let you know. Weird things happen sometimes when you get a higher degree on top. And also, like, holes are not part of this course either, but just letting you know that holes in the graph could occur if, for example, you had something like this. It doesn't necessarily have to be a higher degree on the top. It could be on the bottom too. So say we had this, and this is our rational function, and we wanted to actually simplify it before we started. We know x minus 9 can technically be simplified into x minus 3, x plus 3, because it's a difference of squares if we factored it. And the bottom was x minus 3. So you know what? We could actually cancel those out, and then our equation would just be y equals x plus 3. So what's crazy is it started out like that, and then it ended up like that. So what you're going to get is you're going to get, what's that? That's like a linear equation. So you're going to get a straight line, y-intercept 3. So it looks like that. And then you're going to get a hole in the graph. These guys canceled out. So you're going to get a hole at x equals 3. So where x equals 3, there would actually be a hole, and then it would continue on. And if you're going to test that theory out on Desmos, you sometimes have to actually zoom in the graph in order to see the hole. So yeah, if you verify using Desmos, it won't look like there's a hole there, but if you hold onto the line with your finger and scroll across, it will say something like this on Desmos. It'll be like 3, undefined. So since we canceled these guys out, it actually created a hole in the graph there. So these ones are kind of weird, but you can actually take what looks like a rational function and reduce it to a linear function, and it will just end up having a hole in the graph. But you can expect to not see either of these things on the test.